Good morning friends. Welcome to the video lecture on design of RCC elements. Today we are going to see about limit state design of slabs. Okay, in the previous lecture we have seen about the working stress method involved for singly reinforced beam and doubly reinforced section, and today we are going to see about the limit state method for slab sections. Okay, first of all, what is mean by slab? Slab is an element in horizontal plane, the element in horizontal plane having its thickness smaller when compared to other two dimension. Other two dimension in the sense, if you have taken a box, you have Lx direction, that is length in x direction, whereas length in y direction, whereas the thickness is very small when compared to the length in x direction and y direction. That is called as slab element. Okay, we have two types of slabs in general, that is when the dimension Ly, that is for the longer span, Lx for the shorter span, when Ly by Lx dimension which is greater than or 2 or less than 2. When it is greater than 2 you can call it as one-way slab, when it is less than 2 you can call it as two-way slab. Today we are going to see about the design of one-way slab and design of two-way slab as per the IS codal provision. Okay, this is the slab having the dimension of Lx and the dimension of Ly, whereas D is the thickness of the slab. This is my thickness of the slab, whereas based on the aspect ratio is nothing but we can classify my slab based on the aspect ratio Ly by Lx is equal to greater than 2, you can call it as one-way slab. When it is less than 2, I can call it as two-way slab. Okay, let me come to the picture. I am having slab, this is Ly, this is Lx. Okay, the longer length you need to take it as Ly, the shorter one you can take it as Ly. The load carrying capacity for this element, for this Ly by Lx ratio slab is like so. This is trapezoidal one. This area of load is being transferred to this beam at the boundary, this beam. This area of trapezoidal load is transferred to this boundary. Again, for this end, this is triangle 1 and this is triangle 2. So, the load distribution pattern for one-way slab is like this. Say for example, two-way slab, the load distribution pattern will be 1, 2, 3 and 4. It is separated as 4 triangles, that is in this manner the load is being transferred. Okay, let me see some codal provisions, what our code says. IS codal provisions. First one, effective span. How to take the effective span? First one, distance between center to center of supports, center to center of supports, or else clear span plus depth of slab. Whichever is least you need to take it as effective span for calculating the behavior of your slab, right? Second one, deflection control. As per our IS codal provision, deflection control is span by effective depth ratio. When it is equal to 7, it is for cantilever. When span by depth ratio is equal to 20 for simply supported. When span by depth ratio is 26, you can take it for continuous beams. These are some of the codal provision, how to take the effective span value, then how to check your deflection based on your load carried by your element. Then this is the slab, this is called as edges. When one more slab is there, you can call this as continuous slabs. This is called as continuous slabs, or else only one slab is there. Here this is discontinuous edge, this side you don't have any slab, this side you don't have any slab, this side also you don't have any slab. So you can call it as 3 edges discontinuous and 1 edge is continuous. Or else if the slab is like this, you can call it as all 4 edges are discontinuous. Or else if you have slab here and the continuation of slab here also, you can call this is the interior panel. These classification you need to done to calculate the moment resistance factor for your slabs. Main thing, when a slab is like this, it is being supported on 2 sides, or else it is being supported on all 4 sides also, it will be subjected to failure in this fashion. So it has been restrained, so it has been subjected to failure on this pattern. If it is in smaller size, it will be subjected to this type of failure, that is the failure pattern is in 45-degree angle of inclination. So the failure happens over here in this direction. As of now, we have seen about what is meant by slabs, what is the aspect ratio behind that, then how far the load is being distributed, then the certain codal provisions related to my slab design, then how the panel is being classified as interior panel, to 1 edge discontinuous, other 2 edges are continuous, in like that, then how it fails based on your yield line theory, that is yield line theory or failure criteria of slab. Failure criteria of slab. Okay, now we are going to see about design of one-way slab. Design of one-way slab with following data. First one, clear span 3.5 meter, supports simply supported. Third one, supports thickness 200 mm thick. Fourth one, live load 4 kilonewton per meter square. Adopt M20 and FE 4 and 5. Okay, now we all know about the clear span. Support conditions are simply supported. Then support thickness, we have a wall thickness of around 200 mm. The live load is 4 kilonewton meter. How to design the slab? They didn't give any dimensions regarding this, but they have given you it should be a one-way slab. The design of slab should be a one-way slab. Okay. Step 1. Step 1. Assume D is equal to span by 25, that is 3500, this is 3.5 meter, 3500 divided by 25, I'll get around 140 mm. Okay, then the effective depth small d, effective depth small d is equal to 140 mm. Capital D is equal to 140 plus, assume 10 mm dia bars, so I can write 10 divided by 2 plus 20 mm. I'll get around, this is 5, this is 160, this is 165, I'll get around 165 mm. Then step 2. Step 2 is calculation of effective span. First one, the clear span, that is the clear span 3.5 meter plus the total effective depth, that is 0.4, that is 3.64 meter, or 3.5 plus center to center of my supports. This is my wall thickness, this is my slab. First one, this is the center to center distance, this is the second criteria. This one, first criteria plus this depth. Okay, so this will get around 3.7 meter. So least of two, I'll take effective span is equal to 3.64 meter. Then after calculating the depth, then the effective span will go for step 3. Step 3 is loads self weight is equal to 0. That is the thickness of the slab into 25. I'll get around 4.125. The live load, that is equal to 4 kilonewton per meter. So total W is equal to 9.125. Finishes is equal to 1 kilonewton per meter, 9.125 kilonewton meter. So ultimate load is equal to WU, that is equal to 9.125 into 1.5. I'll get around 13.69 kilonewton per meter. Okay, then I'll go for step 4, moment and shear. Mu is equal to WU L squared by 8, that is equal to 13.69 into 3.5 the whole square divided by 8. It will 3.64. This is the effective span, 22.67 kilonewton meter. Bu is equal to WL by 2, that is equal to 24.92 kilonewton meter. Then step 5, check with Mu limit. Mu limit is equal to 0.138 FCK BD square, that is equal to 54 kilonewton meter. So the calculated Mu which is less than Mu limit. So the section is under reinforced. So I can provide step 6, design. So I'll get around the AST which is under reinforced. I'll go with 0.87 Fy formula to calculate my AST. So AST is equal to 480 mm square. So use 10 mm dia at 160 mm center to center. Then distribution steel provided as per IS 456 is 0.12% of B into D, that is 0.12 divided by 100 into breadth for slabs is 1000 into the depth is 165. So I'll get around 198 mm square. Provide 8 mm dia at 250 mm center to center. So the AST provided will be around 201 mm square. Okay, now step 9, check for shear stress. First one, I know the VU value that is 24.92 we have calculated before. Tau V is equal to VU divided by BD, that is 0.178 Newton per mm square. So I can able to calculate the PT 100 AST divided by BD, it is around 0.17. From IS 456 table number 19, for the PT value of 0.17, I can able to calculate K times tau C, that is the tau C value for the percentage of steel PT. The graph will be like this. For PT, for M20 grade of concrete, I need to take a value of tau C. For tau C, I'll get around 0.35 Newton per mm square, which is this tau C, which is greater than tau V. The tau V value is 0.178 Newton per mm square, so it is greater. Hence, slab safe in shear. If not, redesign the depth or thickness of slab. Okay, then step 10. Step 10, I'll do some check for deflection control. Check for deflection control. So the formula for it is L by D maximum is equal to L by D basic into KT, KC, KF. This is the factor for tension reinforcement, compression reinforcement. This is the factor for flange width of my beams. So this is my LD basic. For again the same percentage of PT value from graph 5, 6, 7 of IS 456, I'll take KT is equal to 1.4, KC is equal to 1, KF is equal to 1. Okay. Now, L by D maximum is equal to 3640 divided by 140 into 1.4 into 1 into 1. So actual is this, that is 3640 divided by 140 is actual for slab. For actual slab I have this 120 for basic is, for simply supported case it is 20. Don't put the actual value over here. L by D basic is equal to 20 for simply supported. So I'll get around 28. This is around 26, which is less than 28. Hence, safe under deflection control. Now, detailing. So, we have done some this is my slab, this is the supporting wall over there. I'll put the reinforcement as, this is the cranking part, this is also the cranking part. Again, one more steel I'll lay here is in this fashion. Okay, this is in the plan view. I'll draw in cross section also. This is my cross section. This reinforcement will be like this, and this is around 8 mm dia at 250 mm center to center. That is distribution reinforcement. this is distribution reinforcement. So this one is about 10 at 160 mm center to center. So this bar is about 10 at 160 mm center to center. This is what the procedure follows for one-way slab design. Okay, now we'll see about the two-way slab. We'll now see about the design of two-way slab. A design of two-way slab for office floor of size 3.5 meter by 4.5 meter. This is my floor size is given 4.5 meter and 3.5 meter with discontinuous and simply supported edges on all sides. All sides are discontinuous. That is, only one floor slab will be there with all discontinuous edges. With corners prevented from lifting. Corners prevented from lifting is that this is all sides discontinuous, so that when we have getting your load, it has been twisted, that is, it will induce torsion at your corners. So you need to provide torsion reinforcement at the corners to provide from lifting of your slabs. Okay, having the live load of 4 kN per meter square, adopt M20 and FE 4 and 5. Let me check first the basic aspect ratio, Ly by Lx. Whichever is larger, you need to take it as Ly, whichever is smaller, you need to take it as Lx. 4.5 divided by 3.5, you will get around less than 2, so it is called as two-way slab. Okay, first step, how to calculate the depth of the slab, that is arriving the thickness of your slab. For in IS 456 code, they have given up to live load of 3 kN meter. So here it is 4. So you should not follow this codal provision. Up to 3 kN per meter square, it is around L by D is equal to 35. Here it is above that. So that's why L by D ratio you can take it as 25. So I'll get around D is equal to 140 mm. Then capital D is around 165. For the clear cover of 20, diameter of the bar as 10 mm. Okay. The second step, the effective span. Here the effective span is nothing but the clear span plus the depth of the slab. So the clear, it will get around 3.64 meter. This is the two steps we have followed for the initial arrival of your size of your section. Okay. Step 3, loads. Self weight, that is the thickness of your slab multiplied by your unit weight of concrete. So 4.125 kN per meter. Live load given it as 4 multiplied by per meter length. So it is 4. For finish you can take 0.6. This 0.6, it is not assumed as the fixed value. You can take anything else if you provide the marble or granite within it. It is based on your floor finish what you are being preferring for your slab design. So I'll take now as 0.6. So it is total load is 8.725. The ultimate should be multiplied by 1.5, that is the factor of safety value. So I'll get 13.08 as my ultimate load. Okay. Then from the page number 90 IS 456 code, the moment resistant factor value, it has been there. MUX is equal to alpha x into WU Lx squared, whereas there I can directly calculate it as for one-way slab it is WL squared by 8. So WL squared by 8, it is get around 0.125 WL squared. Here in both ways the flexure is being created. So exactly I want to know my moment factor, that is 0.125 factor. I want to know exactly, because in this side also the slab is getting deflection, this side also slab is getting, one way it is only one way it is getting your deflection part. That's why I need to go detail into it. So I am going to calculate alpha x and alpha y value from the page number 90 code. From the page number 90 code, you need to check the values of the slab with discontinuous. Overall all the sides it should be discontinuous. For that the alpha x value is 0.007, alpha y value is 0.56. So MUX is equal to alpha x W into Lx squared, MUY also Lx squared. Why it is Lx squared for both the formulas? For calculating the moment value you need to take the shorter dimension. So I'll get two values. Then the Vux is same, WL by 2, that is same. So after getting all these values, I need to calculate MU limit. From the MU limit, I can check whether the depth is safe or not. So the provided depth, that is 165 mm, it is safe or not. So I'll write all these values, then I'll put my values here. MUX formula, I can take it as MU. So I'll get around 69.52, which is less than 140. So the slab is safe for depth restriction. So which is less than, that's why I need to design it as under reinforced section. We'll see the next step. Okay. Step number 6 is about the reinforcement. Now MU is equal to 0.87 Fi AST into 1 minus AST Fi divided by BD FCK. For this, for MUX 13.34, I will substitute here the 13.34, I will get as AST1. So for 980 mm squared, I will provide 10 mm at 250 mm center to center. For MUY 9.5 kilonewton meter, I will take around 213, that is AST2, 10 mm at 300 mm center to center. Where MUX is causing, I need to provide this reinforcement. Where MUY is causing, I need to provide this reinforcement. Okay. Let me check for the shear. Tau is equal to VU by BD, the same formula. For this, I need to calculate PT value. From the table 19, I need to compare the PT value with M20 grade of concrete. So I'll take tau C. So 0.31. The K value for slabs less than 170 mm, it is 1.27. So I'll get K into tau C as 0.39. So which is greater than tau V value. This 3.9 is more. This is the limiting value. This is lesser. So hence it is safe under shear. When it is not safe, you need to redesign your depth of your slab. Then the deflection control. Again the same way, L by D basic value for simply supported is 20. PT you have arrived at from the picture 567, you need to calculate KT, KF and KC from the graph values. Then actual is 26, so multiply all these values is 32, which is less than the allowed value, hence it is safe. Then the distribution steel, for all the distribution it is 0.12% of the B into D, B is 1000 here. While designing for slabs, I need to take 1000 per meter width of the slab. So 198, so I will provide 8 mm at 300 mm center to center. Okay. So this is my 4.5 meter or 3.5 meter. On both the sides, the cranking should be done. This is both the sides, the cranking should be done. This crank distance is around L by 7th distance. This distance is around, at the bottom the distance is around, this distance L 7th, this distance L by 10. So I need to provide cranking on both the sides, this side also. Whereas in one way slab, this bar is straight bar, whereas one side alone we are providing cranking. Apart from that, we need to provide torsion reinforcement in 4 layers. That is here 2, then the bottom 2. So the layers will be 4. The how to calculate the torsion reinforcement is 0.75 times the area of bar in AST2, the lesser area of bar. So 0.75 into 213, you need to calculate the amount of mm squared you need to provide as 4 layers. This is the torsion reinforcement. In all 4 edges you need to provide torsion reinforcement so that the lifting of your slab is being prevented. So this is your main reinforcement, that is 10 at 250 mm. This is for AST1. Then 10 at 300 mm. This is for AST2. This is for Y direction. This is for X direction. Okay. These are some of the procedures for how to design my slabs. Let me come to concluding part of my lecture today. We have seen what is meant by slabs, how it is being classified based on the aspect ratio, then how to design my one-way slab and how to design my two-way slab. Thank you.